Okay, guys. So we were doing 2D Fourier transform. Okay? Before going towards the Fourier filtering, we have to cover some basics. So this is what we were doing. So mainly our focus is the Fourier transform is sampling, that how much sampling is required, and other things will be the filtering in the Fourier. And in between, there are some other things. For example, if I directly take the Fourier transform or DFT, I will get something like this one, which means that the low frequencies are on the edges, okay, and the high frequencies are in the middle. However, it's easier to design a filter if the low frequencies are in the middle. Okay, so in order to do that, I can use the property of Fourier transform, which says that shifting in Fourier domain is actually multiplication with exponential. Okay, and this shifting is a special shift by half of the length of the signal. Okay, so because of that, it reduces to this thing, which is very easy to compute. What I have to do is I will take this our image and multiply with this element by element, and I get this. Now, if I take the Fourier transform, it's basically shifting the spectrum, the low frequency to the middle. So this will help us in building the filter. Also, this looks very nice here because most of the frequencies are low frequencies. So this is also visualization is better. So that's why we are doing it. Okay? And we will discuss the filter design. So there also I will discuss this. Okay, so now design this visualization. Okay, and you can have third one as well because if I shift it, the Fourier domain that I get it is similar to the original domain. Okay, this is also the third one reason, but that's not really important. Okay, so another thing is we also already discussed that the convolution in time domain is multiplication in Fourier domain. However, this is true for continuous domain Fourier transform. Okay, but if you have a discrete, the problem with discrete is it is periodic. It's repeating itself. So the convolution is not directly convolution that we were doing before, but it's a special case of the convolution which we call the circular convolution. What a circular convolution means is that, for example, okay, I have the example. Okay, but the problem is that all the examples, the convolution, the filtering that we were doing was with the simple convolution, which we call it a linear convolution, not the circular one. Okay, so we have to find a way to convert the circular to linear and without disturbing its properties as well. So if I have a signal, I think 1 to 1. Okay, if I just take a simple convolution, I have the filter, I have to convert this with this one. Okay, so how to do this convolution? It's simple. First I have to do reward and then 3, 2, 1, and then I multiply terms like that and assume everything is 0. This is what we were doing before. Origin and starts. You mean this one? Yeah. Okay. Now see, there are two things. One is when I'm talking about the simple convolution, this is general convolution. So I'm not talking where 0 is. We have to multiply and do it. The one you are talking about is the one we are doing filtering, in which we assume the 0 is in the middle. Okay, so that is a special case of the convolution. Okay, so don't confuse yourself. Here I'm just even if you take it as this as 0, no problem. So yeah, this is okay. You will get the same answer. Okay, okay. So this is a linear convolution. Now the circular convolution, since it's a discrete Fourier transform is periodic, so it has to repeat itself, right? So it means that you again have the same thing, and before also you have this. So if I start, this will be multiplied with this, and similarly, if I go here at the end, it will be 3 to 1. Another way of doing it is that I assume that this is connected. Okay, so if this is 1, okay, the 2, 3 is here. Sometimes that is easier, and sometimes it depends how you're thinking. No, it's not padding. It's just a periodicity. Padding we are padding, and here this DFT itself is the yeah, it's the effect of the padding, but we are padding is we introduce it. Yes, you can consider that you pad it, but you did not pad it. Actually. Not mathematically, I will say visualization. You can say that yes, it's a padding, but it's actually not the padding. It's because it's repeating. Okay, but you can consider it as a padding. Similarly, if I move again at one point, so it will be 1, 2, and the 3 will go there. Similarly, like this, and when it reaches here, it will be like when it reaches here 1, and then 2, 3. So it's like circularly. Either you can assume it like this, or you can draw periodically, whatever feasible. Yes. 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 Okay. So now this is circular convolution. However, our actual convolution is the linear convolution of the circular. Like the filters, all the filters we design, we did not assume periodicity or the circular convolution. We assume the linear convolution. Yes or no? Yes. So what we can do in this example in order to make it linear convolution. Yes. So now there the padding comes up. If I just pad this signal by 0, okay, and now assume periodicity, what I will get. Okay, if I do this and start multiplying, I will get the same results as the linear. So this is now the actual padding that I did. Okay, so this is the difference between padding and here you're not doing the padding, but the effect was like offline. Okay, so in other words, what I can do is I can add this much of zeros to make the length of the signal itself equal to a plus b minus 1. What is a? A was the original length, or b is the length of this. Okay, minus 1. So I have to add zeros in order to make the length of the signal equal to this. To make the convolutions equal. Now, if I just spread it, I can take the DFT, multiply them, I get the same effect as the previous filtering. Yes or no? The total length should be this. Okay. So this is I just solved the same example linear. The result is 2, 5, 10, 8, 8, 3. And if I just do a circular convolution, my results are like different, 10, 8, 10, 8, like this. So in order to make the both same, I pad it to 0 and do the same thing, I get the linear convolution. Here, the padding for the circular should be at that. Okay. So what will happen is the case where we have the 2D. Because in order to make a circular convolution equal to the linear convolution. Then here I'm just showing that if I do the linear convolution, my result is this. If I do the circular convolution, my result is this, which is different than what I want. Yes, because here it is 2, 5, 10, 8, 8, 3. Here it is 10, 8, so on. Okay. Yes. Yeah. So in order to remove this overlap or in order to make this same as this, I am doing that. Yes. This is I left it to. So if you see the red one, please try to verify this. Okay. Now, if we do the same thing in image or in 2D, let's say I have this image and I have a kernel 2 by 2, just to make everything simpler. And if I do the linear convolution, how to do this? Assuming this is my 0, 0 location, so I have to pad it on this side, okay, and start applying it. So it's just a diagonal subtraction of the diagonal, right? So it will be 1, okay, then it will be 2, it will be 3 subtraction. Then it becomes here 4, okay, 4, and then 5 minus 1 because we have to invert. Make sure in order to take the convolution, you have to invert 5 minus 1, 6 minus 2, similarly like this, and you get this thing. This is the result of linear convolution, which is our interest. However, when you're doing DFT, what we get is the circular convolution. Circular convolution means here, you see, I did 0, but here I assume that it's a continuous periodic, so there are numbers that are repeating. Okay, if I convert this one with this one, I will get this matrix which is not same as what I want. Okay, in order to do that, what I do the same way, I pad with 0. How many zeros in order to make this a plus b minus 1 and in both directions. So I pad with 0 and then again, if I pad with 0, it means that this is repeating. Okay, so it means that once I convolve this with this, I get this thing which is same as linear convolution. This to show that how we convert circular convolution to a linear convolution. You see, here why I'm padding it because it's a linear convolution. In order to start with this one, first one, I have to pad with 0, like the same way as we were doing before in the filtering. Okay, let's say you have 3 by 3 kernel. How many pads you need here? Padding, you need whole zeros, right? Okay, this was the original one. Now here, this is circular, right? It's repeating. Yes. Okay. But the results are different. In order to make this same as the result same as this one, I have to pad with zeros at the end. Again, what I did, I padded 0 right here. Okay. Once I do this, I will, and then I convolve. Just to summarize, in order to make the circular convolution equal to the linear convolution, you pad with zeros. That's okay. And how many zeros? This matrix along x-axis and y-axis. This is what it means. Okay. Okay. So there are the two things about the Fourier transform. And take a Fourier transform, it's a complex number, right? Okay. So if it is a complex number, it has a magnitude and phase. Okay. So we have to see what is the magnitude. Magnitude is the real square plus the imaginary square. Okay. And angle is the tan, the tangent inverse of the imaginary by real. Just simple. However, we have to, for the images, I need to see that what information is in the magnitude and what information is in the phase. So if I just see the amplitude, if I have the picture and I see the amplitude and the phase, I can plot it, but I have another example that will show you that what type of information these two can have. Okay, so this is just an example that I can plot amplitude and phase. A numerical example, let's say I have image and I take the DFT, I get this matrix. In order to calculate the spectrum for each element, I can just have the magnitude and the phase. Okay, and also if I take the magnitude square, I call it a power or power spectrum. Yeah. This is what I'm saying. This example. See, if you have an image here, so this is a spectrum, this is phase. Okay, but the same image, if I shift it, if you see the magnitude, it's not changed, but the phase is changed. So it means that the information is this information is only in the phase. If I only take the magnitude, I will not get this information. And in images, this information is very important. Let's say if you have a phase, so you have this information in the phase, not in the amplitude, right? Similarly, if I rotation, you can see the magnitude is shifted. Okay, however, the phase is different. So again, for the shifting rotation, the information is in the both. Okay, however, by just shifting it, the information in the amplitude is not there, only in the phase. Okay, and there's not only this, there is something even important, and you can easily see that if I shift it in the time domain is multiplication with exponential. So if I take the magnitude, I have only this thing. So it means that shifting will not affect the spectrum. Yes or no? Yes. Okay. You have this image. This is okay. This is the yeah. Okay. Yeah. So this is the phase angle. Okay, and this is and if I calculate the phase, right? If I just calculate the DFT, this is the phase, and if I calculate the inverse DFT, ignoring the magnitude information and only the phase information, I can keep it. Or in other words, make the magnitude equal to 1, just to see what information is contained in the phase. So what I get is this thing. Okay, so this is only phase information corresponding to the time domain. Okay, what do you think? What is inside? And if I do the same for the spectrum or the magnitude, I get this thing. This is only the amplitude information. This is only the phase information. Okay, so what do you think? Which information belongs to this? For example, for the phase, what are the information I am getting from there? That is the texture information. If you see the texture, you can see it's here. You cannot see an amplitude. In amplitude, you see the variations only, the intensity of the colors. Okay, so the intensity of color information is in the magnitude. If you go further, and in this figure, what they did is they took the phase information of this figure and the amplitude information of this figure and try to reconstruct it. So you can see that since the phase information I put in, so most of the texture information is there, but the color information is not there. And similarly, I do the opposite. Phase information from the previous one, amplitude information from this one. You can see this texture belongs to the previous image more than this. So in other words, to conclude that the phase is giving you these texture informations, whereas the intensity information is in the magnitude. These are some of the definitions we already covered. Even if we covered or not, you have to consider it on this. I'll just leave it. There are some other pairs, DFT pairs. Some of them we did not derive, and some different. Again, go back to the sampling example that we did. In the one we did the sampling example, if you remember, and we say that what aliasing means. Okay, so the similar example that we solved there, I'm solving it 2D. If you remember what is sampling does in the 1D. If I take the samples, okay, so basically I'm multiplying it on impulse rate. Okay, and frequency to make I convert. Okay, so if you remember that example where you have a rectangle. Okay, so what was happening? It was replicating over the impulses. Okay, so same thing we can do, and we can see that undersampling what we can achieve if we do the undersampling. Okay, so just be with me. Hopefully it will be easy. Okay, so let's assume you have a pulse signal in time. Okay, with this. So 2 pi 3 and 2 pi 4 is the angular frequency along the two axes. So it means that the frequency is here 3 and 4. Okay. Now, if I take the Fourier transform, I know that you have 3 and 4 frequencies, right? So this will be a delta function at 3 and 4 in the frequency plane. Okay. And similarly, the replica of this. Okay. Because of the negative part. So I have two impulses at this location because this has a frequency 3 and 4. Okay. So mu equals to 4 and 3, and the same here. So this is Fourier transform of this or the DFT. Yes or no? So now, okay, it's been asked that the sampling frequency is 5 in both directions, 5 hertz in both directions. So if the sampling frequency is 5, it means what will be the impulse train look like in 2D plane. So you have impulses all over, and the difference between them are 5 because the sampling frequency is 5. Okay, in both directions. So you have impulses with a distance of 5. Now, if I want to sample this signal, I have to convolve these two, and convolution means that I have to put this on the top of each of them. Yes, if you still remember the word. Yes, so we have to see if the aliasing is there and what we are recovering. This is what our aim is. Okay. Okay, and the amplitude, if I do this, the amplitude will become 1 by delta t. Delta t, we have already seen this. Okay, because we have infinity here and here, so we cannot put this on every impulse. But for you, just put the 0, 1 and the adjustment of this one. Just focus on this area because others may not be that effective for us. Okay, just plot because it will be very confusing. So what I have to do in order to convolve this with this, I have to put here, okay, 0, 0, then here, okay, then here, then on this one, and all of this. Yes or no? Are you understanding or not? This is completely wrong. Yeah. Okay. So we are not doing anything like complicated. We are just putting all this on the top of each of the impulse, like we did in the 1D. Okay. So it's a bit, it looks like confusing, but it's not. Okay. Okay. So let's go back to the 1D example first. Remember this example? Okay. This is Fourier transform. This is the we proof that this impulse train and this is also impulse train. This is we proof, and we also proof mathematically. Here, the mathematical proof is here that if I'm sampling it, I'm convolving these two. Convolution of these two. Mathematically, we proved it. That is basically putting this on the top of each of them first. This is what we are doing in 2D. Okay, the same thing we are doing in 2D here. Okay, so now these are the impulses. Okay, I am convolving this with this, so it means that I have to put this on the top of each of them. Okay, so this is V, and this is mu. Okay, so let's start with 0, 0. If I start with 0, 0, I want to put that signal on the top of that. Okay, so if you see along B we have 3, 4, 4, right? Along B we have 4 and okay. So it means that I have to go 3 units here, 4 units here, and 3 units here, right? So this is 1, 2, 3, 1, 2, 3, 4. So this is the first one. Okay, the other one will be 1, 2, 3, 1, 2, 3, 4. Okay, if the center is this, yes, impulse at here. Okay, what about this one? If this is my center, so I have to go 1, 2, 3, and 1, 2, 3, 4. Okay. Okay. Again, this will be 1, 2, 3, right? 1, 2, 3, 4. I think so we have B4 and mu it's 3. Okay. So 1, 2, 3, 4, right? And 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. Okay. Now you maybe understand, right? So mu is 3, 1, 2, 3. 1, 2, 3, 4. Okay, so now you have to do it for this and for this. Okay, to get all this, once you do this, you will get all these numbers. Okay, now I said the sampling frequency is 5. So the filter after for the recovery will have the cut of 2.5. Always the cutoff frequency for the filter is half of the sampling frequency. frequency. So if I do the cutoff at 2.5 in each direction, I get these 2 points, and these 2 points are at mu equals to 2 and b equals to 1, and similarly minus 1 minus 2. Okay, so what I recover is half sigma b plus 2 b plus 1 and this. So this is actually inclined domain is equal to cos 2 by 2x plus 2 by 1y. Although we basically transmitted or maybe actually sampled that signal, but we get the other signal. This is called analysis. Yes, you understand? Okay. Okay, so you see what I'm asking means here. Okay, so I think just we finish this part. Okay, the last thing that for the Fourier transform is okay. If you remember at the start, I said that all the 1D signals can be transformed to 2D signals. Okay, so one of the way is using the Fourier transform. Okay, but let's say if I have a 1D signal, I take a Fourier transform or the DFT, but I will get again a 1D signal, right? Okay, but there is a catch to it. Let's say you have a 1D signal, F1, F2 up to let's say 1D signal. Okay, if I take the Fourier transform, I get the same n sample, right? However, I want to make it equal to 2D. Okay, so in order, because sometimes what is happening, this signal is very large. Okay, so it's not possible to take all the samples at once. So what I do, I take window. Okay, so if I take, let's say here, let's say make it 4. Okay, so let's say the window, I take 4 samples, convert to FFT, DFT, I get 4. Okay, then I slide the window again for 4, again can take another another DFT. So what I will get, and I can arrange them in a matrix format. Okay, so what is the size of the? Yes, equal to this. Okay, so now what will be the size of this? And by window size. Okay, so in this way. Okay, so what information I have here and what information I have? So yeah, so here we have the frequency information, right? Yeah, so here we have the frequency information, and here we have the time information. So I am basically what I'm doing is I'm doing the time and frequency together. Okay, yeah, so it will be a matrix. So it will be a very nice matrix showing two things: frequency and time. And in this way, what because most of the, especially most of the neural networks, they are being built keeping in view the images. Okay, so because you have very good networks for the images, so if you are dealing with the 1D signals, you can do a pre-processing, convert to the 2D, and then apply all the methods of the images. Okay, and then apply some of the methods of the processing. That means that you are doing something right. Very common in speech recognition. Yes, it is very common, and also the inside this because the 1D signal, even in the medical signal, EEG, ECG, also they are 1D. And similarly, this is only for Fourier transform, but also if you have let's say Gaussian transform, you can do it. And Gaussian transforms are sometimes better than the Fourier. Okay. So the window size is the hyperparameter. Okay, yeah. So for the window size is the hyperparameter, yes, and also we call it, and it goes just here we are shifting by 1 unit. Okay, but we can shift by 2 or 3 or even with 4, like 4 and then take another 4. Okay, so this is there. So we have no overlap or partial overlap or whatever, and we call this a hop size, that how much hopping we are doing. Okay, so window size plus hop size, it depends on your processing power. Let's say if you have just one hop size, we think that you are taking all the samples, you are taking exact samples, so definitely you need that much processing power. So let's say your power is less, so you can skip some samples. Of course, because of the similarity. Yes, you're right. Okay. So yes, so in some of your projects you are doing, you can try this method instead of having 1D. Just try to do something, even for if you want to recover the compressed signal. So we discussed in very detail the DFT domain. Okay, so now we just try to do the filtering, and I think it's easy once you understand DFT very well. So how to perform the filtering in the frequency domain, and now we came here. Okay, all the way. Okay, so let's briefly discuss. We have an image and we have a system. Okay. So you have an image and you have a system, and in our case, the system was a filter. Okay, so we were convolving this with this to get the output filtered. All right. So if and we call this thing as an impulse response, or sometimes it's also called a point spread function in 2D, because when we multiply an impulse response with something, actually we are spreading it, like the one I just gave you this one. We are spreading it, right? So in some books they also call it point spread function, PSF. Okay. So in frequency domain, let's say I have the frequency domain of the image and also the frequency version of the system, and what will be the output? Output will be just multiplication, because here we have a convolution. Okay, and in frequency domain, this system impulse response in frequency domain is called transfer function. Okay, and the output will be just multiplication of them. In order to get back to time domain, I just take the idea. Transfer function is the Fourier transform of the system. Okay, fine. Okay, now there's one other thing. Let's say you have f equals to 1, 2, 3, 4. Okay, this, and the filter is 1 and 2. Okay, so I convolve these two, right? Okay, just because 1D, I convolve these two, right? Okay, but if I take Fourier transform of this, I will get what? 4 element vector, right? And if I take a Fourier transform, I get 2. Okay, but here the problem is I have to multiply term by term. This is 4, this is 2. So how I can multiply term by term? Yes. In order to make both equal, how to do this operation? Okay, whenever you are short of things, you just add with this. Okay, so what I do, in order this is 4, in order I have to make it 4, and this should be a band. Okay, these type of padding, this one and the circular convolution should be a band always. Okay, I pad here with 0, and then take the Fourier transform of this, multiply it, I will get this, and then I DFT to get it back, and I get the same thing as this one. Okay. So this is what it says. If you have an image that has values up to from x, for x axis you have value from 0 to a minus 1, y from b minus 1. So I have to pad only the impulse response. But sometimes you know what is happening in DFT. You have a DFT method, which is what kernel. Okay, so that kernel is very nicely structured when you have even number, even size of the kernel. Okay, if you have the odd size, then it's not, it's nicely structured, but there are some complex numbers which are like not easy to handle. Okay, so in order, and also the complexity will be more if we do the calculations. Okay, so what we do, we just multiply both of them to make the even. Okay, let's say if your image is 3 by 3, I will make it 4 by 4 by padding at the end for this type of thing. Okay, and then for the, let's say my filter is 2 by 2, I again have to make 4 by 4 in order to make sure that both are equal, and then take the DFT. So this is one of the examples. I have to, what it's doing, it's a low pass filtering, right? So I have this image and I have the filter. In order to do the same operation in the frequency domain, I have to make either, it's up to you. You can make even this 3 by 3 no problem by adding the zeros at the end. But as I mentioned, having the 4 by 4 or the even number of the matrix makes the calculation easy. Okay, so if I pad it with 1 zeros just to make 4 by 4, and here also I pad at the end. Okay, for this type of operation, always at the end. Okay, and then take the DFT of both, multiply term by term to get this, and then get back to IDFT to get the signal back. Yes.
Just to formulate the problem.
To multiply. And if I don't do this, yes.
More specifically, that you find the end.
Because if you don't pad at the end, what will get? It means, let's say I don't pad at the end, this is like at the start, it means that I'm shifting my signal. If I'm shifting my signal at the special domain, it is equal to multiplication by a complex number. So this means that it will be a shifted version, not natural. Okay. Okay. In order to do the filtering, what we have to do is we have to take the image, convert to Fourier domain, and multiply the transfer function, and go back to the time domain. This is the whole process. And if I see the low frequency and the high frequency, I think this is again the same thing that we already discussed. Low frequency will blur the image or the smooth the image. The high frequency will give you the edges, and combination of this will be the original image itself. And this is again some satellite images. This satellite image is showing something here. Okay, so if I take the low frequency components, I can see only the big details. Okay, not the small details. Okay, but here if you see the small details are not visible. If I even try to find out, you can see there are some details are here, which are missing here, right? And this is the Fourier spectrum. Similarly here, if I take the low frequency, it will give me the the low frequencies, okay, or smooth edges, okay. But here, small edges, small details are there. Similarly here, okay. Okay, so I think this is again we discussed it. I have to have the filter, but like Fourier transform the image by taking IDFT, and you get it. It's because the image is always real, right? So even if you do it, you may get a complex number because you are multiplying two complex numbers. So it will not be always a real number. Okay, so in order to get back, I should have a real number. Otherwise, you will have complex number. So make sure when you are just take the real, not that absolute will change the intensity. So take the real one, you get the image back. Okay, so I think we already okay. And so this is the whole process of filtering. First, I take the image and add it with 0 at the end. Okay, and also we have to multiply the image with -1 x plus 1 to make low frequencies at the middle. Okay, this also we discussed. In order to make the low frequency in the middle, I have to multiply with this and then take the DFT and then apply the filter, and then after applying the application of the filter, take it back to the special. Yes or no? This is the whole process. Or connecting all the dots that we do. So what it means, okay? Take the image, add zeros. After adding zeros, okay, after adding zeros, I multiply with -1 x plus 1 each term. Okay. If you will not do this and take the FFT, this low frequencies component with the edges, once just corners, then you have this spectrum. This is my filter, which is called a low pass filter. We'll discuss in detail. Low pass filter, I multiply these two to get this thing. This is the low pass image of the same thing. And after that, get back. So if I get back, I get this image, and I can take this block because the zeros I will ignore. I get this. So it means that I did the smoothing. Why? Because I have a low pass filter here. What it does, it means that high in the middle and low on the edges. It means I'm just taking the, and imagine if I don't do this thing. If I don't do this thing, so how I can make my filter here, like this one, which will be like difficult. So this is the image. This is low pass filter in 3D. What it means, the middle frequencies I multiply with the high and side one. So if I take the Fourier transform of this, multiply with this one, I will get only the low frequency or the middle frequency. And if I convert back, I will get the smooth image. Similarly, this is high pass filter. Okay, high pass means that the center frequencies are multiplied with 0, the others are multiplied with 1. Yes, okay, and convert back, I get the edges, right? And this is actually in between of this. What it's a kind of a high pass filter, but here in the center it's not 0, it's like lower. So what I did, I passed the high, but did not attenuate all the low frequencies, but just reduced them. Okay, so in this way you can see the edges are prominent and the smoothness is also there. So it's in between. Okay, so what are the types of low pass filtering? Let's see in special domain what are the types of low pass filters. How many low pass filters we discussed? One was a simple low pass filter like box. Okay, the other one. So similarly, here also we have one ideal low pass filter. The other is called the Gaussian low pass filter, and then there's a third type which is called the Butterworth low pass filter. Okay, so all these are actually have some properties. We start with ideal. There's some shortcomings. We go to Gaussian, then there's again a problem. Then we go to the Butterworth. Right. So in frequency domain, it's very simple to design. So what ideal low pass filter will look like? Just pass the center frequencies, stop the other one, right? So in this plane, I can say that this is 1 and this is 0. Similarly, but in 2D, I can utilize like this. Center ones are 1, the others are 0, right? If I multiply this with the image frequency transform, I will get the filtered image, right? And you can now see, if I was not transforming it to the center, how would it would look like? As the edges, right? And in the center, it's very easy to write this equation. But if it is on the edges, it will be like a mathematically complex, and also to make this filter, it will be a complex problem, right? So that's why I'm doing the shifting. Okay. Mathematically, I can define it at any point in this plane. If it is less than equal to d naught, okay, this is 1. If the point, any point in this plane is greater than d naught, then make it 0. What is d naught? D naught is the distance from the center to the circle. Okay. Or in other words, d naught the radius of the circle. Okay. So the more radius we will have, the more frequencies we will, and if less, we'll pass the less frequencies. Okay. And what is this point? This is the point distance from the center. This is just Euclidean distance, or the Euclidean distance, right? From the center to any point. Okay. So if let's say I took this point, this here, let's say I take any point here. Okay. So this is my this point. So I have to calculate the distance from the center, and this is this distance. And if this distance is greater than d naught, I will take it as a 0. Otherwise, take it as a 1. Okay. I think it's simple, right? Just take any point and measure the distance. Once the distance there, then you can just, d0 is the radius of the cutoff frequencies as well. Okay. So if you want more frequencies, d naught will be larger. Okay. Now, how practically we do this? What should be the value of d naught? Okay. So I can either do it manually, try, hit and try. Okay, d naught can be 5 or 6 or up to 256 if we have an image of 256 by 56. Okay. Or there's another way to do it. What we do, we take the spectrum, Fourier spectrum, and calculate the power of all the image. Let's say what is the power of all the image? I take this spectrum and add all the values of individual. Okay, this will give me the total power of this. Now I decide my own this area, the circle, and I say that okay, let's say 87% should belong to inside this circle. Okay, so based on this formula, I decide that what should be the d naught. Okay, so how many pixels inside belongs to the low pass? So it's a kind of a ratio, inside ratio to the total ratio. So you can fix d naught and see that how much energy I want and how much energy I want this circle.
I decide what's the amplitude percentage.
Yes.
Then I come up with
Yes.
the naught.
And yes.
Then I apply
And apply the low pass filter. Okay. Fine. So if I do the same thing, like for example, how much percent? This is 30%, which is too high. Then I go to 7.2%. Okay. Then I go to 4.9%, and then 2.6, and this is 0.6%. So in this way, based on this percentage, I am doing the filter.
Percentage like a scale.
Yeah, the more percentage you have, the more ones you just actually discard it. Okay? Yeah. However, if I consider this ideal low pass filter, it has a problem that the inverse Fourier transform of this ideal low pass filter, inverse Fourier transform in time domain, this is the filter. If I take the inverse transform, IDFT, I get this thing. And this, if you see, there's some, because you see what I'm doing, I'm multiplying this with my image. So in special domain, I am convolving this with my image. So if I convolve this with my image, it has a problem. You see this effect? There's some ringing effect in this. So this is the problem with the ideal filter. The ideal filter will create the ringing effect, right? Yes or no? Okay. So if I just take one slice of this, I will get this. Okay. So yes, kind of a sink which is not actually a sink. It looks like sink. It's called a Bessel function, but anyhow, this is the same as a sink. Okay. So this will create the ringing effect. So that's why we go to the Gaussian filter. Gaussian filter. The good thing is about the ringing effect is not there. Okay. And I know that the Gaussian is this thing. Yes or no? This is a Gaussian formula, right? And d square u v is actually d square plus u square plus v square, right? So this is the distance from the center, and here sigma square is the spread, right? So this is basically, in the previous we call it d naught. So that's why I just sigma square I just considered it. So d naught is the distance from the center. Okay, so the more spread we will have, the more yes, cut off, of course. So that's why original formula for the Gaussian is this one, but I use d square because d square we were using previously, just to make sure this was the cutoff. For example, d naught is small, it means the spread is small. Here this transition is small. So the Fourier transform of the previous ideal filter creates some ringing effect, whereas the Gaussian is the Gaussian in time is the Gaussian in space. Okay, so it will not create any ringing effect. However, the only problem is that this roll-off factor, we don't have much control. This is not a disadvantage, but this is one of the shortcomings of the Gaussian low pass filter. Okay, so because this slope, we don't have any. We can either make it like this or make it like this. But let's say I want to make it another way, keeping the same, but I want it to be like this. So I cannot do it. So that slope is not our control. Okay, not fixed, right? Okay. So for that, this is just again the same thing using the Gaussian low pass filter. Okay, so then it comes to Butterworth filter. It's also a very simple filter. Just 1 divided by 1 plus this by this, and you can see that this, if this term becomes more, okay, if n becomes larger, okay, this becomes large, and the whole term becomes small. Okay, so as n increases, this becomes small. So this is the low pass. It has inverse relation between them. Okay, so because this and this has an inverse relation, which means that as this point goes away, this will become less. It's a low pass filter. Right? But here we have more control. I can, for a fixed d naught, I can change the shape as I want. But here, if you see, For the fixed D naught, I cannot change the shape. So here I have more control. Plus, if you see for the larger value of n, this is more closely resembled to the ideal low pass filter with a sharp cutoff as compared to the Gaussian. So this is one of the advantage of the Butterworth filter. Okay. So I think that's it. But again, the problem even with the Butterworth is that when n becomes very high, still you will get the ringing effect, but it will not be so severe for the as compared to the low pass filter. Okay, so still I will say that this filter is like in between. Yeah, so Gaussian and ideal low pass filter. And also, yeah, this is just an example that how the digits, there's some discontinuity in the digits. So if I apply the low pass filter, I get the continuous image. And similarly, if I have you see the wrinkles, so it can be, and this is how the filters work in our mobile. Okay, this is just a simple example of the filters that we have.